Hello everybody. So we are back now from average gradient. Okay, we're back from the differentiation rules and all that stuff. But I want you to remember what we've done in average gradient, your gravy. You can tell I'm hungry, man. Okay, but at the same time, if we look at the points, right? Okay, so let me take a gradient like I did the last time, right? At some point, let's say that this point is somewhere like here. Whoa, that is not a straight line. That's not a straight line. Here we go. Okay. So let's say that we have some line like that, or let me make it a little bit shorter so that it's like that, okay? And then that is going to be at this point of intersection and this point of intersection. But let's focus on this as the main point, okay? Remember that what we had was this was the point x, and then this was the point x plus h from our average gradient, such that what we had was f of x plus h over here, right, at the point x plus h, and then here as the output for x, it would be f of x. But now what I want you to focus on is what happens. Can you see that this is clearly, I'm gonna show you now, clearly this is the distance from x to x plus h, which is just h units. Okay, so this is h units apart from each other. But what happens if we actually shorten this distance each and every single time? So what happens if I do this? If I'm going to take the h and make it a little bit shorter, like so. So let's say here, somewhere here, right? So let me put the h until here, such that what we're going to have is, let's suppose this is our new x plus h. Okay, I know that this is obviously not the same as this, but this is for example purposes. This is our new, so let's call this h1 and let's call this h2. But h2 is smaller than h1. Okay, so I'm going to write here h1 is bigger than h2 in this case over here. Okay, such that what happens, we need to lead the point up now. So x plus h2 is going to give us f of x plus h2, right? And this would be h1. All right, there's a lot happening here, eh? But what do you notice? If we take the tangent from that same point here, from this point that we have, and intersect it through there, so we need to actually make sure it does intersect properly, so it'll look something like this, right? It's going to get messy, I know. What do you notice? The point is getting closer and closer and closer to x. So what's going to happen if we take this purple line, right, and we are going to take it closer and closer and closer, like this, for example. If we take the purple line, that just means that now our new h is going to be somewhere here. Meaning our h is going to get smaller. So this would be called our h3. Okay, so let's call this h3. So from here, what do you notice? We are getting closer and closer to getting a tangent, which is obviously just, the tangent is where it only intersects one point on the function. And the secant line is basically this line, the blue one, where it intersects 2 points on the function. Same with this purple one that we have here. But the whole idea of this is we're taking the gradient and we're trying to approach the h towards 0. We are trying to have basically no distance to get an approximate tangent. A tangent that is so perfect that it is literally the gradient of the function. So what we are saying is, from our information, we know the gradient is equal to what? It is equal to f of x plus h minus f of x, all divided by h, if we remember from average gradients. Okay. But remember, our whole idea of the derivative So I'm going to say here, using the derivative, and the derivative, I'm going to say here, I'm going to give its definition. What color should I use? Green. The derivative is just the gradient at a point. That is the definition of a derivative. The derivative is just a gradient at the point. Using the derivative definition, this then finally implies to us that the gradient is just going to be equal to the derivative of the function. And this is the same as the limit as h approaches 0. Remember, our h was decreasing over the time all the way to as close as 0 as possible of the function f of x plus h minus f of x divided by h. Okay. So this is the definition of the derivative. It is just the gradient at a point. So it's the gradient at some point over here. Okay. And we can call this point whatever, but we'll get into that application later on. For now, let's learn first principles. And this is how we derive the formula. Our gradient is our average gradient is essentially getting as close as possible to the actual gradient, but we're just approaching 0. Also, because I don't like fractions, or you know what, I'll get into that in the actual example. But just know that this is what we are going to be using as our definition, and note that it is always going to be the gradient. But then once we find the point, we plug it in, and then we actually find the gradient. But anyway, let's get into the first example and see how we apply this properly. I just only derived the first principles. I didn't actually this is not going to probably be a question, but it's good to know, to explain. So yeah, let's get to the first example. Crazy. Alright, so here's the first question, and this is going to be the only question I'm going to ask, and then I'm going to let you do a question afterwards on your own. You need to use the first principles to find f prime of x if f of x is equal to x squared plus 2x plus 1. Okay. So in this case over here, what are we going to do? We need to use the first principles. And what is the first principles? We know the first principles is that f prime of x, the derivative at a point on f, is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now this is the one thing where I usually write it simpler. Because I don't like working with fractions and it gets all sloppy, the way I write it is the following. I can just write it as this. So still the limit as h approaches 0, but notice that we can take out the h as a 1 over h. And then we can write it as f of x plus h minus f of, let me write that properly, f of x. What did I just do? I just took the h outside as 1 over h, basically. So you can see that. And clearly we don't have to work with fractions at this point, like a lot of fraction work. It's much easier to read. So the first thing is, what are we going to do? What do we need to actually find, and how are we going to progress with this? First of all, we need to know what f of x plus h is going to be equal to, and we need to know what f of x is going to be equal to. We already know what f of x is equal to. It's all of this. But we need to know what is f of x plus h. F of x plus h, this is how we are going to find it. So first things first, f of x we know is equal to x squared plus 2x plus 1. But we need to find f of x plus h. So f of x plus h is just equal to, we replace all x with just x plus h. So it's x plus h raised to the power of 2 plus 2 into x plus h plus 1. Okay. And then there we go. That's all we're going to have from here. If you want, you can obviously simplify this as much as possible. I always recommend doing this, by the way. If you're able to do it, do it. So x plus h squared is just going to be x squared plus 2xh plus h squared plus 2x plus 2h plus 1. Okay. And this is what we have. Now we can just plug all of the stuff straight into our derivative formula, or our first principles formula. So this implies to us that f prime of x is just equal to the limit as h approaches 0 of 1 over h of f of x plus h is equal to x squared plus 2xh plus h squared plus 2x plus 2h plus 1. And then we're minusing that by what? F of x, right? By f of x. And f of x is equal to x squared, and don't forget about the bracket, x squared plus 2x plus 1. Okay. And then from here we just simplify. Keep simplifying as much as you can. So the limit as h approaches 0 of 1 over h into x squared plus 2xh plus h squared plus 2x plus 2h plus 1 minus, take the negative into everything, we have x squared minus 2x minus 1. And then what happens? What cancels? The x squares will cancel each other out. Can you see that? What else cancels each other out? The h squares can't cancel each other, the 2xh doesn't, the 2x's can, because 2x minus 2x gives us 0, and then 2h, there's no other thing like it. And then what we're going to have, we are going to have 1 will cancel out with a negative 1. So what are we just left with in the simplest form? We are just left with this being equal to the limit as h approaches 0 of 1 over h of 2xh plus h squared plus 2h, and that is what we are left with. Now what? Now we can just multiply 1 over h into every single term. Every single term we multiply 1 over h. And then what are we going to have? We are going to have the limit as h approaches 0 of what? It's going to be 2xh over h plus h squared over h plus 2h over h. Okay. And then this is equal to the limit as h approaches 0 of, and then we can see the h cancels here, the 1 square cancels with the h, so therefore we're left with h to the power of 1, and the h's cancel here. And then what are we left with? We are just left with 2x plus, and then we're going to have h plus 2. And now with the limits, in order to get rid of the limits, we need to substitute the h into wherever h exists. The reason why we couldn't sub in h immediately from the beginning was because it's in the denominator. So that will give us an undefined answer. So that is why we simplify from here. And then we get to a point where we can plug in the h value. So let me rather say over here. Then therefore we can plug in the h in here, such that this is just going to be equal to 0. And then what we're left with, the limit falls away since we already took in all the h's equal to 0, and we have 2x plus 2. And we remember that f prime of x was what we used all along. So therefore, f prime of x is just equal to 2x plus 2. So that would be the derivative of the function x squared plus 2x plus 1. Now let's verify this using the techniques of differentiation. So I will call this verification. Okay. Using the rules that we know about differentiation. So what is the function that we have? We have f of x equals to x squared plus 2x plus 1. And we need to take the derivative on both sides. So d by dx of f of x, if you don't know what I'm talking about, go to the rules and notation for differentiation. That is what I'm using this for. Which is equal to d by dx of x squared plus 2x plus 1. And then here, the derivative of f of x is just f prime of x. And this is just equal to the derivative of each and every single term, which is going to be what? D by dx of x squared plus d by dx of 2x plus d by dx of 1. Okay. And then to finalize the answer, therefore, we can say that f prime of x is equal to the derivative of x squared. Notice we're going to use power rule, where n is equal to 2, and that will be n times x to the power of n minus 1. So that's 2 times x to the power of 2 minus 1. Plus, this will be 2 multiplied by the power rule using this. The derivative of literally the variable by itself is always just going to be 1. You'll see that the exponent is going to be 0. So that's why it would usually be that way. And then we add it by the derivative of any constant is just 0. So therefore, f prime of x is just going to be equal to 2 times x to the power of 2 minus 1, which is just 1. So it's just 2x plus 2 times 1, which is 2. Can you see that this answer is the same as this answer? That is how you actually check whether what you did was correct. And that is just the first principles. Now I will just give one question for you to try out by yourself, and then from there we will move on to another topic. Okay, so here's your question that I want you to do. I want you to use the first principles to find the gradient of g of x is equal to 2x cubed minus 5x squared plus 4x over x at the point x equals 1. If you listened in the beginning, right at the end of my explanation of the derivation for this formula, you would remember what I said. So that is your hint in order to find the actual answer. Good luck.